minus squared. So now, what you see is term by term. You have the same denominator, same sum. Term by term, you had this a squared plus b squared over 2 here, a plus b quantity squared over there. Consequently, this guy is bigger than mu n. It's happening just over there. But how much bigger? It's bigger as equality. By exactly this thing, the difference between the a minus b divided by 2 quantity squared. Okay. Let me compute a third statistic. So I have now two statistics, the mu and the mu. Let me compute a third one. Let me go to be theta. Theta is going to be the following. So theta n is the following thing. Function on the IW S such being, well, this should be a function of also epsilon and set or delta. I count how many mediocre channels are there, and divide by total number of channels I have on that column. This is the fraction of mediocre channels, mediocrity measured by this delta. Okay. This is delta mediocre, the fraction of the mediocre channels. Okay. So now, if you take a look at this particular sum here, okay, each channel, which is delta mediocre, contributes at least a couple of delta squared to the summation. So this mu n plus 1 is bigger than mu n plus this each of these mediocre channels, they contribute to this sum. At least kappa delta. The non-mediocre channels, I don't know how much they contribute, so I lower one up by 0. Okay, this contribution to this squared, so I have this. Right. Good. So this inequality here. So now what we have found is the following thing, that this mu n, this second moment of these columns, it is an increasing sequence of numbers. Are they bounded from above? These increasing sequence numbers, these mu's, are they bounded from above? By 1, because each of these mutual informations that I'm averaging is a number between 0 and 1. These are mutual informations over binary input channels, so they can never exceed 1. Consequently, these mu n's are increasing, therefore bounded by 1, they must converge. Okay. If they converge, the difference must go to 0. All right. So the difference goes to 0 means that this quantity must be equal to 0. This is a constant, does not depend on n. Only way that it goes to 0 is that theta n goes to 0 and then gets large. So consequently, so we have this. So we write this thing now. Implies 1 plus 1 goes to 0 and then large. This is 0. So this means that the for a fixed delta. Okay. So no matter what your notion of mediocrity is, okay, if you count a fraction of mediocre channels in each column, that fraction goes to 0. So at the end, you end up with no mediocre channels. So this polarization transformation, this thing here, eventually depolarizes the region. So no mediocre channels left. And secondly, by the fact that this mu is a constant, the average is preserved, okay? Which means that the fraction of good channels must be exactly IW. So we have to take a look at if you define good channels, let's say alpha. Bad channels. Same thing. Okay. So if this goes to 0, since the average mutual information is preserved, this guy must be going to IW. Original base channel that you started off from, okay, and the limit of the beta and fraction of bad channels must be the remaining fraction. Okay. So there's the good, bad, and the ugly, okay, and the good, bad, and mediocre. Okay. The mediocre disappear, okay. Nobody is left of the ugly channels. Okay. IW fractional channels that we create are good. Remaining ones are bad. Okay. So what we have seen so far is that the polarization does happen, and this process, the thing that we saw on the computer with the BEC, is not some accidental phenomenon. It is happening for any channel that you want. Okay. This might be a reasonably good time to stop because I think I took more than 1.5 hours until now. But I can be short at the second part. There's nothing there. In the meantime, are there questions that I should address right now?
Whose approach is this to showing polarization?
No, this is what I made up.
Sorry?
This is what I made up. This is I think Andy Lulliger asked me a question some years back, and he wanted to teach this thing in class. But if you take a look at Erdal's, I'm terribly sorry, I'm not crediting anyone at this moment. So this whole polarization construct is due to my good friend and colleague Erdal Arıkan. In fact, he's the reason I became an information theorist. So I'll tell you the story later on, perhaps when we come back from the break. But if you look at his paper which introduced polarization and polar codes, he uses a martingale argument to show that the polarization happens. Martingale is a very elegant things. Everybody should learn them at some moment. But if you want to teach the polar codes to the, let's say, senior undergraduate students of the communication department, or whatever, the department, you don't really want to pull out martingales from her hat at the time of the most crucial part of the thing. Say, okay, martingales. So Andy was asking me, okay, you have something which is elementary. So this is what I came up with, a long flight from Zurich to Boston or something like that. Something reasonably equal to this. So this appears in a paper of Navina Al-Sam and myself, and my PhD students who recently graduated, showing polarization in a much more general context. So this idea of taking a look at the second moment is helpful to prove polarization in not just of stationary number of channels, but also non-stationary number of channels. If you started from W1, W2, W3, and then you combine them in W2, W2, W3, etc., and then you combine the stuff, etc. Then will this polarize or not? Yes, for the same reasons.
Maybe it might be worthwhile just writing down the name of the reference you just gave.
I think
Yeah.
I think there's something.
All right, as Emre just indicated, maybe this is a good time to take a break. We'll meet again in 15 minutes, so that would be, is that okay?
Even more if we rest in the lower transfer.
Okay.
If I could hear, essentially, this is the most important that we already covered.
Okay.
Even going to be 18 about this time, without doing something.
Okay. So let's say we'll meet again at 11 a.m.